Everybody for having me. Please don't hesitate to stop me. I sort of had a fair bit of internal debate about the right level to pitch this talk. So if I went too high or too low, please let me know. Okay, so this part maybe sounds fancy, but it only sounds fancy because it's not that worth worrying about. So in physics, we often define quantum field theories by looking at maps from one space into another space and trying to do some kind of Feynman integral over the space of all such maps with respect to some measure. Okay, obviously I'm not going to write down any of that stuff here, but sort of the important point is one of those spaces you might map into is just a vector space, but in this case, it's going to be a quaternionic vector space. And the reason it's going to be a quaternionic vector space is I want a hyperkähler structure. And the only hyperkähler metric that anyone actually knows how to write down is the flat one on a quaternionic vector space, which I can also think of as T star of n. And then there's another operation which you can do to quantum field theories, which is gauging by asymmetry. Now, this is, it turns out that physicists knew about stacks 100 years early, because that's really what gauging is it's the physicist's way of thinking about stacks. So this is, I'm looking at maps into this guy, and then I say, no, I want to look at maps into some kind of quotient stack. And physicists understand how to think about that using this operation of gauging. So what this gives us is some kind of physical gadget. Let's not worry too much about what kind of physical gadget it is. The important thing is the kind of things it takes in are through manifolds. Actually, the only three manifold I'm ever going to worry about is R3. There probably is some interesting story involving interesting three manifolds, but it's definitely not a part of the story that I understand. And it has a lot of supersymmetry. And that having a lot of supersymmetry means that there are two pieces of the theory that we can get our hands on much more mathematically, where from the supersymmetry, they come these things called topological twists, which is basically adding an extra differential to my theory and only thinking about the cohomology. And the interesting thing is there are two ways of doing that, called the A and B twists. Let's not worry about what they are, but if you've heard about the A model and the B model and homological mirror symmetry, that's a story about 2D sigma models into Kähler manifolds. And this is some upgrade of it, where we're thinking about 3D models and hyperkähler manifolds. The hyperkähler is somehow forced on us by upgrading from 2D to 3D. So for one of these twists, for one of these theories, the moduli space of vacuum, I probably should have, having these moments of oh, right, I should have mentioned that. So the moduli space of vacuum, what that means is I look at spec of the Hilbert series assigned to S2. So if I have a 3D TQFT, the Hilbert space I assign to a two-sphere is a commutative ring, and I can take its spec. Now, if I had, the kind of topological quantum field theory that most mathematicians like, this would be finite dimensional, and the best I could hope for would be to get a finite set of points. But in this world, I'm instead getting things that are extremely non-dualizable, and I get very interesting algebraic varieties as this spec. And this is telling you that this is sort of a field theory that's way, way far away from our actual real world. Because in the actual real world, there's one vacuum, we think. We assume, at least. Whereas this guy has some wild, complicated moduli space of vacuum. I just wanted to emphasize that this is sort of, it is something that's kind of a concrete part of the TQFT, but it sort of doesn't show up in very much in the usual way that people think about TQFT. That's telling you, I called these TQFTs, but they have a very different flavor from most of the ones you would have seen before, like, the ones coming from quantum groups. Okay, so for one of these twists, this space, so this is what's called the Higgs branch. If I put the B twist here, this is called the Higgs branch. And that's a space we understand reasonably well. It's gotten by taking this flat hyperkähler manifold and doing a hyperkähler quotient. And this was shown, I believe, in the very early 80s in this paper of Hitchin, Carl Hede, Lindström, and Holacek. And one of their main motivations was to come up with interesting examples of hyperkähler metrics. There were very, very few that were known at the time, and this was sort of a reliable way of finding such metrics, or spaces with such metrics. It's still kind of hard to describe the actual metrics. You can prove that they exist. On the other hand, this other twist, the A twist, this gives you something that's called the Coulomb branch. And that proved much more mysterious. They sort of knew that it was there, and there were some examples where you could compute what it was, but it seemed like a very strange object, and somehow the operations you had to do to get it were very strange. What physicists would tell me, when I was early in this game in the early 2010s, is they would say, oh, well, the Higgs branch is the same if you compute it classically or quantumly. And so you can do a classical computation, which gives you this hyperkähler quotient, and that's somehow still right for the quantum field theory. Whereas the Coulomb branch, you can do the classical computation, but you get something dumb that's obviously not what you want. And so you have to do some quantum corrections. They would say, oh, there are corrections to the hyperkähler metric, and this somehow causes the underlying topology of the space to change. And I would say, well, what do you mean? And they would be like, oh, it's kind of complicated. And I would say, you're right. Okay. But what this sort of classical thing ultimately tells us is that this space, well, the classical computation gives me, I take the torus of my group, I take its Langlands dual, I take the cotangent bundle of that, and I mod out by the action of the biogroup. And you'll note here, there's no dependence on n. So that's obviously a really bad answer. I'm supposed to get something that tells me something about this quantum field theory, and the only thing it tells me is what's the gauge group. So that's not a great answer. And they would say, oh yeah, well, you have to do some modification to this. And it turns out, if you want to think about this as a mathematician, you would think, oh, actually, this is a complex algebraic variety. I'm only going to think about one of the complex structures in my hypothetical hyperkähler metric. And in that complex structure, well, I get some algebraic variety that's birational to this quotient, but not isomorphic to it on the nose, where I've done some modifications at this point. And one way you can think about that is sort of there's a modification of the structure coefficients in the multiplication. We'll sort of talk about different ways to think about this. So a helpful way to think about this is if I look at this T star of the Langlands dual, well, what do functions on that look like? Well, I have the functions on the cotangent fiber. So that's the symmetric algebra in the dual of the Lie algebra. I always forget I can be writing on my iPad, which was the whole point of bringing it. I have this symmetric algebra, and then on this dual, Langlands dual torus, right? The way to think about what the Langlands dual torus means is characters on T check are co-characters of T. So every co-character of T can be thought of as a function on T check, which is the actual character. So I get a basis for functions on here, which is all the polynomials in T star times these co-characters. You can think about it as a group algebra of the co-character lattice if you want to. And then when I act by W, what restriction is that putting on things? Well, if I had the trivial co-character here, then I would just be requiring that my coefficient in T dual was W invariant. But if I have a non-trivial action on this lambda, well, then I can, as long as I choose a polynomial that's preserved by the stabilizer, I can then sort of spread that out over the whole orbit. So the kind of rough picture to have in your head is I need one co-character from each orbit. So let's say a dominant co-character, and I get to multiply that by an element of these symmetric polynomials, functions in the dual of the Lie algebra, symmetric under the stabilizer of that co-character. Now again, you'll note here, no dependence on n. So this kind of size of the representation, it always has this description, and you can think, there are various different ways of thinking about it. One way to think about it is I kind of deform how I multiply these guys. So then there was a lot of work over the early part of the 2010s. This work in physics by Cremonesi, Hamani, and Zaffaroni, and by Bullimore, de Mofta, and Garo, and then by Sasha with Finkelberg and Nakajima, which sort of brought this into clearer view. So when I say this guy is birational to T star of T check W, well, all that means is if I look at functions on this guy, it's an affine variety. So it's determined by its ring of functions. That's a subring of this fraction field. So inside this fraction field, there's a subring, which is the functions that are regular on T star of T check. And I don't want quite that subring. I want some weird little modification of it, where I remove some elements and add some new elements. And we'll talk about sort of what happens in specific cases. The idea here is roughly that instead of just having this co-character, I have to multiply that co-character by certain rational functions that depend on lambda. And roughly, the gauge group G tells me what denominator I need. So that's how I tell the difference between an abelian group and a non-abelian group with the same torus. And the numerator depends on the representation. So as I sort of throw in more weights in my representation, I get a sort of gradually smaller and smaller and smaller subring. All right, are there any questions? So this is just sort of the rough shape of what we're looking for. Okay, so again, as I said, I kind of debated what things I should cover in this talk. You know, I kind of took a talk that was aimed at a slightly more specialized audience and was like, oh, I should mention that. So one thing I should mention is what is this definition, right? I started out by being like, well, physicists wouldn't tell me what this object was. And then, well, Sasha's paper came along and he told me, here's what it is. Here's definition of this ring. And that definition, I'm going to rephrase it a little bit, but it was sort of geometric. It was kind of an affine Springer theory story, where I would take my representation and take my group and think about replacing those with their Taylor series and Laurent series versions. So, right, my G is going to be something like GLN. And before I was thinking of GLNC, now I'm going to think of GLN of C square brackets T or a GLN of C round brackets T. And I want to look at the quotient N mod G for the Taylor series version or the Laurent series version. So again, you know, we were gauging things. Secretly, that was thinking about stacks. So this is some really horrible stack where I'm modding out an infinite dimensional variety by an infinite dimensional group, but it'll be okay. And the way you should think about this is I'm taking spec of Taylor series, that's a formal disk, and I'm looking at the space of maps of that formal disk into the quotient N mod G. And then similarly, I look at the same thing, but with a punctured formal disk. And you can interpret, you know, what's a map into N mod G? Well, a map into point mod G would be a principal bundle. So a map into N mod G is a principal bundle and a section of the associated bundle for N. So when I write down this quotient, that's really what I'm thinking about. I'm thinking about either on this disk or punctured disk, I have a principal bundle for G, and I'm taking a section of the associated bundle for N. And I can take a fiber product of these guys. And what does that mean? That means I have one copy of the disk, I have another copy of the disk, and the map from this guy, which is principal bundles on the disk, to this guy, which is principal bundles on the punctured disk. That's what this bottom guy is, punctured disk. This is the unpunctured disk. Means I'm taking the principal bundles on the two copies of the disk, and I'm identifying them away from the origin. So away from the origin, I'm gluing these guys together, and I'm making this thing called a raviolo. So interestingly, this fiber product I can think of as bundles on the raviolo with a choice of the associated bundle for N. And if you sort of think through how that works, this is the kind of a very weird little scheme, but it is well defined. This section, it's going to be determined by its value on the punctured disk, but I have to check that it's holomorphic on both origins. And so I might have taken something that's holomorphic on one of the disks and then done an identification away from the origin that messes up it being holomorphic. But a good exercise to do when you want to think about this is that if I just looked at principal bundles on the raviolo, so principal bundles on the raviolo, what I get is G round brackets T mod, well, let me just write G of O, mod G of O on both sides. So G round brackets T identifies two copies of the principal bundle on my two different disks away from the origin. And then acting on the left and the right by G of O does the change of trivialization. All right, great. So whenever I have a space that I've written as a fiber product like this, its Borel-Moore homology gets an algebra structure. So I can look at the Borel-Moore homology of this guy. I have to do a little bit of work to kind of make sure that's well defined. The kind of North Star to keep in mind is I want the diagonal to give me a Borel-Moore class. So I want things that are sort of finite dimensionally different from the diagonal. And this is not just an algebra, it's actually a commutative algebra. And that's a little harder to see. The rough idea you should have in mind is that when I want to multiply two things, instead of kind of taking two raviolos and layering them together, I could take one raviolo and puncture it in two places, and then I would be able to swap the points. So somehow, what's really happening here is I have some multiplication, which is really a three-dimensional thing, and I'm restricting it to a two-dimensional slice. But in the three-dimensional world, the points can go off and swap. They don't even need the 3 dimensions to swap. They can just swap this two-dimensional guy. And so this is slightly harder to think about because there's no such thing as a formal disk punctured at two different points, but that's kind of the picture you should have in your head. And yeah, what you have to say is yada yada factorization. So somehow you think about doing this on actual curves where you can take two different points and then think about what happens when the 2 points collide. All right, cool. So I have a commutative algebra. Well, I want to take it to spec, right? As I was saying, this moduli space of vacua, if you're a mathematician, the way you want to think about it is your TQFT, it has a space of local operators. That's the Hilbert space assigned to an S2, right? It's the things where I can go to any point, I can cut out a little S2 around that point, and I can insert it in. So the spectrum of that is going to give me this Coulomb bridge. Okay. So this is sort of a cool approach to coming up with this algebra. There are lots of things which are manifest by thinking about the geometry of this space that might be hard to see otherwise. But I find it sort of hard to process. You sort of tell people this and their eyes kind of glaze over as they sort of think about this infinite dimensional moduli space of principal bundles. And so, I want to talk about how you think about this more concretely. Okay, so if I achieve anything in this talk, it should be like you coming out with a slightly more concrete idea of what this thing is. Now, maybe one reason why this again is one of these things of like, oh, right, I should mention that. One reason these are important is, well, most often we want to think about the quiver case. So this is the group and the representation, which would give you a Nakajima quiver variety. So that's obviously an interesting group and representation to consider. And taking the Coulomb branch for it is like taking some alternate world perspective on the Nakajima quiver variety. So, finding the Nakajima quiver varieties like secret imaginary friend. So one nice guy you can cook up from this is the nil cone of GLN. That comes from the quiver. It's a type A quiver. And I didn't incorporate this in sort of let me not worry too much about this, but there are quiver ones you can write down. They give you the nil cone. This one's interesting because the Nakajima quiver variety is also the nil cone. But you can come up with more interesting things like Slotovy slices in type A. This is the quiver that would give you T star of a partial flag variety for GLN, or maybe a better way to say this would be a smaller nilpotent orbit of GLN. As the Higgs branch, you instead get a Slotovy slice as the Coulomb branch. And you can also get these symmetric powers of C2 monocyclic group. And it's maybe not totally obvious from my poor drawing here, but this is a loop, an edge. So it's going from this guy back to itself. Well, so from here to here. So Nakajima quiver, right? Those are the hyperkähler quotients. No, I'm taking the Coulomb branch. So if I took the hyperkähler quotient, this would also give me the nil cone. I'm doing this Coulomb branch, yeah, this guy, right? No problem, understood. So yeah, it's interesting because geometrically it's in a totally different space. These cases might fool you, but for example, the dimension is always twice the rank of the group. So like adding extra edges to your quiver, well, that doesn't change the rank of the group. It doesn't change the dimension of the space. It does some weird birational transformation to it. So it's a very different thing from this sort of story of taking the quotient. And you can have situation, right? Like, for example, if you put in the group and the trivial representation, the quotient is something very bad and kind of stacky, right? Whereas the Coulomb branch is a nice, smooth, positive dimensional thing. So it's a sort of strange story. So it's the universal centralizer. I'll get to that eventually. Okay. So, sort of silly to do this without doing some examples. And I wanted to talk about a few kind of explicit cases where you can get your hands a little more on what's happening. So first example, if we take just C star with the trivial representation, I get something very simple. I get the cotangent bundle of C star. And what's happening here is, well, I told you I wanted the symmetric algebra and the dual of the Lie algebra, so that's this variable T. And then I wanted the group algebra of the co-character lattice. So that's an M and M inverse. So I get a copy of usual polynomials, I get a copy of Laurent polynomials. That tells me I'm getting T star C star. And it's T star because I'm getting one coming from the dual of the Lie algebra and one coming from co-characters. Okay, great. So let's generalize this. What happens if I take n to be a representation of C star? So the functions on this Coulomb branch, I should have screwed this up. I was supposed to put that this is the coordinate ring of the Coulomb branch. That's going to be a subalgebra of this ring, of this polynomials tensor Laurent polynomial. And the subalgebra, as I told you, is sort of you have to kind of modify the multiplication, but when you're trying to put them inside the same field, that means you modify the generators. So now I have generators. I still have T, that's fine. Sort of always keep my copy of sim T. But the things corresponding to co-characters change. So what before was the function corresponding to a co-character gets multiplied by a power of T. And that power of T is the sum of the positive weights for C star acting on it. And similarly, the guy going the other way, the inverse, gets multiplied by minus the sum of the negative weights. So this Q minus Q plus minus Q minus, this is the sum of the absolute values of the weights. Of C star. So that's what actually determines the structure of the variety, is just the sum of those weights. But just ends up being important for me that it's embedded in this way. You want to sort of think about the relationship between different groups and different representations, and then it's actually important to remember this. So we get ultimately this relation that when I take m plus times m minus, I get a power of T, which is the sum of the absolute values of these weights. And as a variety, I can describe that as C2 modulo this finite group, the cyclic group, whose order is the sum of these absolute values of the weights. And this inclusion of this guy as a subring, that has a geometric description. It's induced by the map on spaces, which is forgetting the end section on the Raviolo. So if I'm thinking about these maps into stacks, it's induced by the map from n mod g to point mod g. So it sort of comes up naturally that I have such an inclusion, but I can then algebraically think about how to get that subvariety. Okay, any questions? And since it will be important later, let me kind of zoom in. How does my space change? So before, I had my sort of line with T being my variable, and the fiber over every point was a C star. And now what happens when I do this modification? So if T is not 0, nothing changes. So now I have my pictures, here's my T, and I have my C stars, but I should think about sort of these C stars kind of shrink a little bit. And then over T equals 0, I get something really different. I get the union of the two coordinate axes, right? Think about if Q is 1, I'm getting the map from C2 to C, which is the product of the coordinates. So if the product is non-zero, I get a copy of C star. And then over this exceptional fiber, I get two components. And if I wanted to think about what this subring was, one way to say what it is it's the stuff that doesn't have a pole on either of these components. That's how I end up having to multiply by these powers of t. That's the power of t I need to consider to get rid of the poles. Okay. Let's generalize a little bit. That was a commutative case. What about a non-commutative case? What if I take PGL2 or SL2? So roughly, I should get the same thing as if I had taken C star and then mod it out by the action of W. So W is my vial group. If I'm in PGL2 or SL2, it's a two-element group. And it acts on co-characters by the multiplicative action, by sending M to M inverse, and it acts on T by the additive action, right? This is a co-character, this is an element of the Lie algebra. So the element of the Lie algebra gets negated. All right, cool. So there's an approximate here because what's happening is these guys are birational, but they're not isomorphic. It's not exactly the quotient. So in this case, where I have PGL2 acting, well, S swaps positive weights and negative weights. So this guy I was calling Q plus and minus Q minus before, those have to be the same. So now I just have one Q. My capital Q from the previous page is twice. Okay. So based on this Q, what do I get? So this guy is, well, I have T squared. I'm taking invariance under the action of the vial group. So T is not invariant anymore, but T squared is. I want to have that guy. And then what do I get from my co-characters? I want to kind of emphasize here, this guy is just what happens when I symmetrize the element I had before. Let me flip back for a moment. I have this guy, M raised to what would now just be the Q. There's only one Q. So I have M raised to the Q and M inverse raised to the Q. So if I just symmetrize those, this M circle is what I would get. So I get one extra thing which is unexpected, which is, well, instead of symmetrizing, I can anti-symmetrize them, right? This has a plus, this has a minus. Plus, minus. But then the anti-symmetric thing, well, that's not in my ring, so I have to divide it by T. So that's something that wasn't in my coordinate ring for the abelian guy, if I'd put in C star, right? I'm doing an extra thing, I'm dividing by T. So again, I'm doing something that's going to be birational, but kind of mess up the structure. And that's this -1 here. Right, and you can explicitly write down the equation relating these guys, and this is in the original BFN paper. All right, and then if I have SL2, something very similar happens, but there's a subtle difference. So this M circle is what I was calling M bullet before. And I have this guy where I symmetrize, but then I divide by T squared. Yeah. So you're asking, like, how does one prove that this statement is true? Well, I mean, roughly one goes and reads the correct lemma on BFN. So in the PGLN case, it's actually not very hard because right, this is the monopole operator corresponding to the fundamental guy in the affine-Grassmannian of PGL2. And there's an explicit formula for what that is, and this is just exactly what that formula is. And then this guy is the dressed monopole operator, dressed by T. And then roughly what happens is, right, the fundamental, the smallest co-weight in SL2 is twice the smallest co-weight in PGL2, right? So the reason I'm getting this -2 here is roughly, this is like the square of this guy. So that's the kind of picture to have in your head. This guy is not the monopole operator on the nose, but you can subtract stuff in t² from it to make it the monopole operator. Somehow, if I wanted to write down the specific monopole operator, it's a little more complicated to get right. So yeah. If I were going to try to adjust it, if you look in the sort of BFM paper, they kind of just say, oh, well, I know these basic algebraic properties of this guy, it has to be like this. I could probably prove this more carefully. There's a paper of mine where you can construct the monopole operators a little more constructively so there's this sort of annoying thing that this is sort of supposed to be the square of something, but there's no co-character in PGL and SL2 that this co-character is twice. But there's a bigger category where you can factor this guy as the product of two morphisms, where the thing in the middle is something different. And I could get this formula from that. That's probably how I would justify it if I needed to really do so carefully. All right. Are there any other questions? All right. I know these are a little bit funny, but they're very important calculations because sort of really all the information is in here. You know this, like the information on the past two slides. Well, you proved this.
No, but what do you mean by what do you call all the information?
I'll get there. I'll explain it a little more carefully. All right, so as I say, you can use this to kind of fix all the behavior in all cases. So how do we do this? Well, we have this torus, and the Coulomb branch always has a map to the torus mod W, right? So if I have T star of T dual, that has a map that's just project onto the cotangent fiber. And it turns out that map carries over. When you think about it geometrically, these are just the equivariant parameters for an action of G. All right, and away from the hyperplanes where roots and weights of n are 0, this preimage exactly behaves like this classical case. So sort of all of the bad stuff is happening along these hyperplanes. And if you look at the generic point of one of these hyperplanes, I missed a parenthesis there, you get something that looks like, let me be a tiny bit vague about that looks like something smooth times one of these rank 1 Coulomb branches. Where if I'm on a hyperplane where no root vanishes, I get C star, and this is kind of the C star coming from a generic point of that hyperplane, and where you get the PGL2 or SL2 story if a root does vanish there, and it's the PGL2 or SL2 that comes from that root. And I'm always getting the Coulomb branch for this subgroup and the weight spaces that vanish on this hyperplane. So I always can kind of reduce to these ranked 1 cases. And to answer Sasha's question more comprehensively, because in his paper, they prove that this guy is normal. So if a variety is normal, I'm an element of the coordinate ring if I don't have any poles on a V divisor. Right? One way to say this is if I have something that's normal, it's the intersection of all the DVRs that contain the coordinate ring. Where the DVR is just the things that don't have a pole on that particular V divisor. And so if you want to understand the V divisors, well, you have the ones that come from this open locus. That's exactly the same as this sort of boring story. And then you only have a few more. Over every one of these hyperplanes, you have a finite number of them. And these calculations on this page tell you what they should be. Right? So in this case, where I don't have any roots vanishing, I have two Weil divisors sitting over my hyperplane that depend in this way on the weights. And in this case, I usually only have one, but there are a few weird degenerate cases where I have two. But basically, you look at these formulas and you set t to 0, and you see like whether the thing you get is a domain or whether there are a few cases where it's not a domain. All right, great. So we can sort of prove stuff about this Coulomb branch by just thinking about all of these DVRs. And most of the DVRs just kind of come from thinking about this open locus, and it's nothing different from, there's no dependence on n. There's not even really very much dependence on G. And then there are a few interesting ones where we have to pay attention to what's going. Okay, I'm keeping an eye on the time. Okay. And there's a useful trick with this story, which is that we can deform our Coulomb branch. So this is what's called flavor deformation. The usual way I want to do this is I want to take G and I want to replace it by a bigger group. It still acts on the same representation that contains G as a normal subgroup and such that the quotient is a torus. So the most common example, which you can do for any group, which makes it kind of convenient, is I can take the group and then I can multiply it by the scaling C star. So that's a bigger group. It contains G as a normal subgroup, and it still acts on N. And this is, if this bigger group contains the scaling C star, we call it massive. This is Telemann's fault for using this term. But he thinks of this as sort of adding some extra masses in your physical theory. And the thing that's nice about this is I never have to worry about weights and roots vanishing on the same hyperplane. All the weights have weight 1 under this C star. All the roots have weight 0 under this C star. So I can never have the same hyperplane that corresponds to both of them. All right, and I can do a deformed Coulomb branch, which is just, well, this space now carries an action of F. So I just do everything equivariantly for F, and that throws in a copy of the equivariant cohomology of a point for F. So a polynomial ring. And I get a nice little deformation of my Coulomb branch. And I should say, right, I mean, this sort of story, you can see immediately how to generalize this story. Right now, I just put tildes on my Lie algebras, right? And I do exactly the same local stuff at hyperplanes. But now I get to go to this page and say, oh, I only need to worry about the case where Q is 0. I'm never going to have to deal with having non-trivial weights vanishing on the same hyperplane as a root. So that makes me happier. It makes my life easier to do this. Okay. And maybe we'll talk about this, and then I'll quit for the second half. So again, this is one of these, oh, I should mention this. There's this very interesting paper by Bielavsky and Foskalo, which gives an actual geometric interpretation of the points of the Coulomb branch. And I have a slightly funny restriction, which is, I have this kind of behavior near every hyperplane, and it's okay if I get roots vanishing on the same thing as weights, but I need to only ever get PGL2. If I get SL2, this theorem isn't correct. But if I always get PGL2, then the Coulomb branch I can actually think of as an open subset of, take the Coulomb branch for the torus. That has an action of the Weil group still on it. And I look at there's a projective variety, which is the W Hilbert scheme. It's the set of all W invariant subschemes, which are isomorphic to the group algebra as modules over W. So if I have a free orbit, that gives me 1 point in this guy. But then there will be points where I have non-free orbits and something a bit funny happens. I have some funniness about what the subschemes are. And it turns out you can think about MGN as an open subset of this. So there's a really nice way to think about this, which is, so this open subset, it's the subschemes which push forward to subschemes on T star mod W. So they call this the transverse Hilbert scheme. So I have this map from Tn to the Lie algebra of T. So when I take a subscheme here, I can push it forward to T, and I get a coherent sheaf there, which might be the structure sheaf of a subscheme and might not. So I look at the open subset where I actually get a subscheme there. And then I have to look at the part of that that's in the closure of the free orbits. There are some other weird components of that I want to ignore. All right. So I can think of every element of the Coulomb branch as one of these subschemes. And the kind of key observation, and I have a little bit of time, so it's okay, is so what does it mean that I get a subscheme down here? It has to be a copy of the co-invariant algebra, essentially. So this is one of these theorems that sort of sounds amazing, and then when you actually, once you sort of understand how this W Hilbert scheme works, it becomes very easy. Yeah, I didn't write this down. Now I'm sort of struggling to see whether I can actually explain it quickly enough. Let me just say, this property of being a subscheme down here, it exactly sort of corresponds to whenever I have a function on this C of M Tn, then I can anti-symmetrize it and divide by delta. So this sort of comes out of the fact that, like, if I get a subscheme down here and it's sort of concentrated on one point, then it looks like a copy of the co-invariant algebra, and the anti-invariant stuff, it gives me a Frobenius trace on it. Sort of everything can always be picked up by anti-invariant things. So I have to throw in functions of this form. And if I look at this Coulomb branch for PGL2, that's exactly what I did. I took my monopole operator in the abelian case, a function on the guy in the abelian case. I anti-symmetrized it, and I divided it by delta, which in this case is just T. And the fact that that's what happens for PGL2 tells you as long as you only get this PGL2 behavior, this sort of carries over, and you always get this Hilbert scheme story. All right. So maybe this will be a good place to pause. And slightly worrying that I apparently have way too many slides, even for a 2-hour talk, but we'll see. We can go get some cookies or something.
They notice eventually?
I think I got Nick's attention while I was going up the stairs. We'll see.
That's the time you can teach us all the secret math that you don't want them to know.
There you go. Well, I mean, are there any other questions from the first?
It's maybe a general questions like, so I can think of one of these deformed Coulomb branches, like the example you gave where I just had a scaling action, and speaking like the quantum Coulomb branch, like, right? Like it's going from the classical into the quantum, maybe.
That's slightly different. So if you want, there's also a quantum one, which I haven't said anything about. And in order to get that, you come here and you add a C star here. But the point is, it's the loop C star, whereas this F is induced by an action on N mod G itself. So there's sort of some similarities, and because a lot of what makes things work is just sort of formal stuff about equivariant cohomology, and you get to apply that as well. But the way it deforms the relations is different. Right, so a kind of important consideration is like, when you think about these examples, what the flavor deformation will do is like deform T. But and inverse and T will also commute with each other. Whereas turning on the C star equivariance makes T and M no longer commute. It becomes the differential operators on C star instead of the functions of the cotangent. Okay. All right, great. Okay, let's assume I should just restart. All right, great. Okay, hope everyone enjoyed their cookies. Now let's maybe try to speed up a little. Okay, so in the case of the torus, the Coulomb branch has a sort of extra interesting structure that I think somehow is still a little underappreciated, even though many people know about it, which is if I think about this as the Lie algebra times this dual torus, I can think about it as a group scheme. It's a group scheme over T. When I say group scheme, that means every fiber is a group and, in a kind of consistent algebraic way. So, for example, if you want to think about a Hamiltonian action of this dual torus, it's really maybe kind of more natural to think about this whole group scheme acting, right? You have the moment map, which goes to T, because I'm looking at the Langland's dual torus. So if I have a Hamiltonian action on something, I can think of that as a T scheme and think of this T group scheme that's acting. And then when I do Hamiltonian reduction, what does that look like? It looks like I just replace this product with the fiber product and then push forward by modding out by the null fibration. So this becomes a Lagrangian correspondence between MT0 times X and X. So there's a version of the story that's true for all G. If I take the pure Coulomb branch, so that means with the trivial representation, that's a flat abelian group scheme over this quotient. So the generic fiber looks like T check, and then something a little bit funny happens when I go to these hyperplanes and the group's structure changes. There's a nice way to think about this, which is I can think about the Langland's dual group. So T check is the torus of the Langland's dual group. And I can think of the Lie algebra mod W as the dual of the Lie algebra of this Langlands dual group, mod GL. And there's this constant section. So there's a map from the T mod W into the dual of this Lie algebra, whose image is a slow-to-be slice to the regular nilpotent. The thing you should think about, if this is all a bit too fancy, you can always think about the GLN case, in which case what's happening is this usual construction of a matrix with a fixed minimal polynomial, right? So I can put zeros on the diagonal, ones on the row below the diagonal, and then the coefficients of my polynomial in the last column. That's the constant section in the case of GLN. So it always constructs a matrix whose minimal polynomial and characteristic polynomials, the polynomial that comes from this last row. So, right, that means I'm thinking of this quotient of Cn mod Sn as the degree n monic polynomials, where the elements of Cn are the roots. And so modding out by Sn is just only remembering the polynomial and which not which root is which. So in general, MG is I look at this constant section, right? And I look at an element of T mod W, I look at this constant section, and then I look at the centralizer, or the stabilizer in the coadjoint action of this constant section. So in GLN, what does this mean? This means I think about my point in Cn mod Sn, I think of that as a polynomial, I think about the companion matrix of that polynomial, and my fiber over that point is the centralizer of that companion matrix. This is the regular centralizers. So if your roots are all distinct, then the fiber is a torus. It's the stuff that commutes with a diagonalizable matrix. But if all of them are the same, in fact, this centralizer is, I lied, it's not unipotent because it's got the scalar matrices in it, but it's the scalar matrices times a unipotent thing. So basically, as more points come together, this group becomes more and more and more unipotent. All right, so I'm only going to be interested in products of GLNs, so that's sort of all we need to know about the pure case. But how do we incorporate this representation? So there's a very interesting way to think about this, which is, well, if I have a weight, I can think of that as a linear function on the torus, and I'm using this deformed torus. It doesn't really change anything to think about the deformation. I can also think about that as a co-character from C star into T check. And I do this kind of wacky thing, which is compose these. So I start on the Lie algebra, I map to a scalar, and then I have a rational map into T check that's going to blow up and not be defined if my weight was 0. So this is a perfectly good map on the complement of the hyperplanes where the weights are 0. So generally, it's a rational map. And I can take these for all the weights in my representation, and I can multiply them together. When I say multiply them together, I'm using the group structure. This is all happening in sort of the pure case. So I can think about multiplying these together using the pure guy. And so it defines an automorphism of this open subset, where I have T check, and then the open subset of the torus, where none of the weights are vanishing. I mod out by W. All right, and there's a theorem of Coulomb. This is a little bit modified version from my paper with Tom Gannon, that if I don't have any pair of weights such that one is a negative rational multiple of the other, so I can avoid this by assuming that my G star is massive. This is what Coulomb does. He just adds in this scaling C star, and then this can never happen because every weight has weight 1 under the scaling C star. If that happens, then you can describe the functions on MGN as the intersection in the functions on this open subset of the preimage of MG0 under 2 different maps. So this is an open subset of MG0, so there's the obvious map of restriction functions. And then I can also do that and twist by this automorphism epsilon. So what I'm doing is when I apply epsilon, I'm sort of changing the degree to which things have poles or zeros when they go to these hyperplanes defined by roots. If you want to say this in a more geometric way, you can say there's a push-out diagram in the category of affine schemes, where I take two copies of MG twiddle. If I don't put a representation here, that means the representation is 0. And then I glue these two copies along this open set and find the unique affine scheme that this like really weird non-separated scheme maps into. And this is just, again, sort of describing the ring of functions on here by sort of saying what happens when I go to these bad divisors. All right, so for example, if I take C star again, if I'm acting on Cn by weight 1, I'm multiplying by t to the n. And so if I look at these functions, let me not try to go through the details here. It's going to look like the C star picture we had before. But what we get is we have a coordinate t and we have a coordinate s. And I want the pullback to be regular both when I pull it back by the obvious inclusion, which is just sending t and s to t and s, but also when I pull it back by this twisted inclusion, which is sending t and s to t and s t to the n. So when I sort of follow this through, I found that the subring I get is generated by t to the n times s and s inverse. And again, this is C2 mod C mod NC. So what's happening here is, I had shown you this picture where the exceptional fiber had two components. And the two components come from, the one comes from the pure case, and the other one comes from the pure case twisted by this automorphism. That's what you're sort of supposed to be picking up here. All right, and this is why I had this weird restriction on the signs, because if I had things of positive sign and negative sign, then I needed both my positive guy and my negative guy to have their power of t boosted up. And sort of this picture can only boost up one of them, depending on what the signs are. All right. So one nice result of this is it shows that our group scheme MG acts on MGN for any n. Right? If you go back to this picture, well, MG acts here, MG acts here, MG acts here. And these maps all commute with the MG action. I'm multiplying by a rational section of MG, and MG is a commutative group. It's abelian. So that commutes with the action. So there's an induced action on the push out. Right? There's a really weird push out in the category of arbitrary schemes where you glue this guy together and you get something really weird and non-separated. MG acts on that, and now I'm just taking the aphorization of that weird scheme. All right. And one thing that, well, I doubt you guys have any insight on, but you never know. This should have some physical meaning. Somehow it should be something about this story about D modules on the affine Grassmannian. But the fact that when I look at the pure Coulomb branch, that acts on an arbitrary Coulomb branch. All right. There's a generalization of this. Yeah, maybe I'm not sure either. The physicist should know what it is, right? Like, I don't know, when I talked to Hanani about this, he has no idea what this group structure is, like what it's supposed to mean. right? That's my kind of, so something that Hanani would understand. Which is, on some level, a low bar for a physicist understanding something, but which also can be somewhat demanding. All right, there's a sort of generalization of this when I have two groups. So I have G, I have a reductive subgroup H. So I can look at the pure Coulomb branch for G, I can look at the pure Coulomb branch for H. And I want to say that this guy for G acts on this guy for H. If I think about just the tori, right, I can set up my maximal tori so that the maximal torus of H is a subgroup of the maximal torus of G. So dualizing, the dual torus is a quotient. So this is kind of the picture you should have in your mind of, if I look at my H, I should be able to sort of extend this map to the whole family. All right, so this lets us do a kind of interesting thing. If we have a space that MG acts on, we can kind of smash it with the Coulomb branch. So what does that mean? I take the fiber product, oh, whoops, that's a mistake. I take the fiber product over this base with the Coulomb branch MGN, and then MG acts on the whole thing diagonally, and I mod out by that. I'm doing everything in the category of affine schemes. So when I mod out, that just means look at functions, look at ones that are invariant under the group, take spec of that. And that's my balanced product. And we have this nice functoriality theorem that if I take MH and I smash it this way with MGN, I get MHN for the restricted representation. I should warn you, in the current archive version, there's an extra hypothesis that we needed. I now think we have a proof without that hypothesis, but the proof is still kind of in progress. So in the gluable case, the proof is actually really simple. It's basically you take this diagram and you whack it with balanced product. And gluable is basically exactly the hypothesis you need for this story to work correctly. The main issue is actually compatibility with pullback to C of H. So you sort of look at what would you need for that pullback diagram to still work after you base change with C of H, and that's like literally exactly what this extra hypothesis gluable we added is. But I think we now know, yeah.
Any assumption on H here about
H is a reductive subgroup of G. Yeah. Yeah, I mean, the in progress is to cover my ass a little bit, right? So we have this gluable condition where we're definitely a bit more certain about the proof. I mean, this is like something I was working on last week, but last week I was happy with the proof, so.
I'm confused about this product. I mean, have like a subscript and a superscript.
So the subscript is fiber product, and the superscript is mod out by the group. Yeah, right. So it's, yeah, if you sort of somehow the way to think about this, right, is that MGN is symplectic. All of the fibers are Lagrangian, and so this is sort of like, yeah, you should think of it as like a Hamiltonian reduction, but somehow the groups over different moment values are different. All right. Yeah, I know.
I mean, so this whole thing is uncharted, right? So basically.
Yes, right. Sort of both pieces together. So if I take this fiber product, this is basically modding out by the null filtration, the null fibration, I should say.
So you don't need H to be of the same rank.
No. No. I mean, our main motivation was things like H is the diagonal of G. But, somehow modding out by mg and then having the g here, the sort of dimension of g cancels. All right, let me just sort of give a really brief sketch of how I at least claim that we're able to prove this. You want to exploit normality. So normality tells you that if you have a map between normal affine algebraic varieties, you only need to show that it's an isomorphism away from a closed subset of codimension greater than or equal to 2. So actually, I think the hardest part is to show that this balance product commutes with base change. So if you prove it for the flavor deformation, you can then base change and conclude it in the undeformed case. And after you do the flavor deformation, right, you have this nice property that you never have roots and weights vanishing on the same hyperplanes. So I need to prove this at generic points of hyperplanes by normality. That's sort of the only place I need to worry about it. And if I'm on a hyperplane where weight vanishes, it reduces to the abelian case. If I'm on a hyperplane where root vanishes, it reduces to the pure case. And those cases are kind of easy. The abelian case is covered in the original BFN paper, where you can think about doing Hamiltonian reduction by flavor symmetry. And the pure case is just kind of obvious. Like if you get rid of G, this is just a tautological statement that I multiply by the group and then I divide out by it and I get the same thing back. All right. So as I say, I think the hardest part of this is actually making sure that balanced product commutes with base change. So, I'll update you when I'm a little more certain that's true. Okay, so what kind of cases do you want to apply this in? What would be interesting settings in which you could do this? Like, right, it sort of sounds a little bit silly. We're like, well, how are you going to benefit from making your group smaller? But of course, you might start with a bigger group where you understand what's going on and try to reduce to a smaller one. So in particular, one kind of application I had in mind was if you take a quiver, as far as I know, this operation didn't exist before, but I want to take a quiver and I want to cut it into pieces at vertices. I call this a dismemberment. This is like when you have a chicken leg and you're cutting through the joint. So I have a quiver where I keep the set of edges the same, but I break up vertices. So I might do something like, here's my graph, and I would kind of cut open here and switch to having this. And what does this do to the quiver gauge theory? Well, since the edges stay the same, the underlying representation is the same. But I'm making more vertices, so I end up with a bigger group. So I fix a dimension vector on my Q0, I pull that back to this Q0 check, which is my dismembered graph. And if I take the product over all the vertices of the GLNs in this Q check, there's an obvious inclusion of the G for the product over the original graph. And sort of for the guys lying over a given vertex in the original graph, this is the diagonal map. All right, yeah, maybe I should have just said. So, if I look at M Q check of N coming from the quiver gauge theory, exactly what this is telling me is if I take this guy and I do the balance product, so C of G Q A check M G Q check with M of GQ, this will describe MQN. So this is saying I can start with the Coulomb branch for my broken up quiver. I can do this reduction operation to it, and I can get the Coulomb branch for the quiver where I've stuck things all together. So for example, I could do something like take a graph and literally pull apart every edge separately. And then I would only have to understand the Coulomb branches for a single individual edge, which you can do by some work of Nakajima and Takayama. And then I need to sort of stick those together using this reduction process. So one particularly nice case is to think about having a graph, whatever's going on over here. Here I have an edge with label n, and then I want to think about sticking on a leg where I put n, n-1, n-2, n-3, etc., all the way down to 1. So when I do that, turns out there's a really nice description of this. I take the Coulomb branch for the smaller graph, and if I sort of follow through the description of all the Coulomb branches for the pieces, I'll find what I do is I take the product with GLN, not base change. The base is like already built in here. So I'm supposed to take GLN times the base and then base change over the base. So the base just disappears. And mod out by this M of GLN. So the way to think about this is because of this, wait, not that, this vertex with label n, I have that MQ already maps to this base for GLN, which I can think of as the degree n monic polynomials. And part of the structure of the Coulomb branch I mentioned before is on the fiber over each of these polynomials, I get an action of the centralizer of the companion matrix. So what I'm doing is each of those fibers I'm multiplying by GLN, and I'm modding out by the action of this centralizer. So I get something considerably bigger, which comes from the fact that I have all these extra vertices now. And so, for example, in Hanani's work, he quite often uses that when you do this, you get a GLN action. And this gives you a very nice description of that GLN action. I'm using left action by these centralizers to take this quotient, while I still have the right multiplication by GLN. All right. And more generally, if I do this with the a dimension vector that's sort of falling faster, I get a similar description, but I have to incorporate the Slodovy slice for a particular nilpotent. This guy still has a Hamiltonian GLN action, where the moment map is I take my companion matrix and I commute it past my element of GLN, and then map that to the Lie algebra. So this is sort of saying I take the pre-image of a Slodovy slice under that map. All right. Cool. So you can view this, there's a sort of story of Moore and Tachikawa for understanding Higgs branches of what are called Sicilian theories for GLN. So those are things which you can describe as the Coulomb branches of these comet-shaped quivers. And in the physical picture, you have a Riemann surface that has punctures. You have some data attached to the punctures, and you're trying to assign a space to that. And these legs and the dimension vectors along the legs tell you what's happening at the different punctures. And then I have G loops here corresponding to G, the genus of the surface. So let me not sort of try to go into all the details of this. We're all pretty tired at this point, but I think it's obvious how using this kind of dismemberment story could allow you to give a sort of more systematic description of these guys. So I think the thing that's really new here is sort of exploring this idea that you use only this universal centralizer, not the action of all of GLN. So if you read the earlier physics papers on this stuff, they'll sort of have two legs on here with corresponding GLN actions, and they'll kind of have those legs annihilate each other and sort of interpret that as a Hamiltonian reduction by GLN. And in our picture, instead, you can just glue together two vertices, but that means you have to do this reduction by MGLN instead of all of GLN. So more in Tachikawa have this picture where you think about this as like a TQFT valued in Hamiltonian spaces over a group, where the groups correspond to punctures, and gluing two punctures together is a Hamiltonian reduction, whereas somehow to an unpunctured point, you have an action of MGLN, and doing this balanced product is doing a connected sum. It's making a new puncture at the point at 2 points and then gluing them together. All right. So in general, this sort of thinking about this sort of inspired us to try to give a description for more general Sicilian theories. Ooh, and I forgot a minus sign here. So if I want to take the Higgs branch for a Sicilian theory with a single puncture labeled by a nilpotent, what I have to do is I have to think of pairs of elements of my group, elements of the regular Sloterdijk slice, and then when I look at minus add G acting on them, that should be in the Sloterdijk slice for the nilpotent that's describing my puncture. And this regular centralizer acts by right multiplication, by multiplying on X. Great. So I can sort of act in a way that preserves this guy and changes this guy inside S reg. Okay. Sorry, changes G. Right. Okay. And on the other hand, if I have an unpunctured surface of genus G, there's a nice description of this guy in terms of taking a bunch of copies of the adjoint representation of G check. And I'm sorry, I switched from writing LG to writing G check. Those are the same thing. Sometimes I use one, sometimes I use the other, and I wasn't careful enough about being consistent. All right. So when you think about this idea of doing connect sums, then this tells you how to sort of assemble all of this. So in the GLN story, this is actually a theorem where you can take all of these pieces corresponding to sort of the genus G part, and then all the punctures, and think about doing a big connect sum of all of them. And each of the connect sums is taking this fiber product, and then I have to mod out by a bunch of copies of M of GLN. So in order to kind of get everything right, I have to think about having a big tuple of guys in this M of GLN, and their product has to be 1. That's to account for the fact that I was supposed to take the product with MH. Right, and this space has a pretty natural description. All right, and since I wrote everything just in terms of centralizers and Sloterdijk slices and all of this stuff, I can conjecturally, I don't know what it means to conjecture this, because I don't know if we have a precise description in other types, but this should be how you describe the Higgs branch for general Sicilian theories as well. I'm running low on steam here, but let's talk about it. Are there any questions? Okay. Yeah, I know. We're all pretty tired, but there's a few more applications. So our original motivation for doing this was Tom had been at PI in October and asked me about this problem, and we suddenly started going down this road rather rapidly. For various reasons involving the story about implosion, it's very interesting to think about, take a group, take the radical of a parabolic, mod out the group by the radical of the parabolic, take T star of that. So that's not an affine variety, but it's an open subset of an affine variety. It's quasi-affine. So you can take its affine closure, and it's very interesting to try to understand that guy. And for GLN, this parabolic, well, it's going to correspond to some block diagonal matrices, and we can actually describe this as a Coulomb branch. The Coulomb branch corresponding to, well, this is actually a Sicilian theory. I have n-1 here. I take my n and I break it up according to the blocks of this levy, and then everywhere I just go down by decreasing by 1. So I do that here, decrease by 1, decrease by 1 on all of these legs. And this is interesting in part because we hadn't known before that this affine guy had symplectic singularities, which Coulomb branches always do. And we hadn't known that it had a finitely generated coordinate ring, which Coulomb branches always do. And it was known that the sort of obvious guess you might make for the coordinate ring of this guy, that it would be generated by functions and the vector fields coming from the left action of G and the right action of L, is not true. Those are not generators for the coordinate ring, but sort of going through this Coulomb branch story, you get some bigger set of things, which actually are the generators. All right, so that was actually our main motivation, but I think this stuff about more general Sicilian theories is more interesting. And I just wanted to mention, in part because this had sort of come out of some conversations I had with Sasha earlier, there's sort of another kind of interesting way to think about this, which is when I take the Coulomb branch, I'm just for convenience, I'm taking, of the product of two groups, I can think of this as the cohomology of a ring object in the Satake category of G, which, some of you know better than I, but could think of that as like constructible sheaves on the affine Grassmannian. So by the derived Satake equivalence, I get a Hamiltonian G space, GL space. And I know I should say it's like a derived stack or whatever, but let me just think of it as a space. So we know how to get the Coulomb branch from this guy, which is we think about the map to the dual of LG, and we pull back by the constant section. So I think one kind of interesting thing about this story is it suggests how to undo this operation, how to start with the Coulomb branch and reconstruct this X. And it suggests that all you should do is multiply by the Langlands dual group and then mod out by these centralizers. There's a question mark here because I definitely don't want to claim that we proved this. But I think it's probably not actually that hard. I don't know. And I certainly think it's an interesting conjecture. All right, so I think that is all my slides, amazingly. The conjecture is that if you want the object that corresponds under derived Satake to the ring object, what you should do is take this Coulomb branch, think about.
You have G and H, and so N is the representation of G times H.
Yeah.
Okay, and so you want the ring object for on the affine corresponding of G times H.
Yeah, and then I push forward to G. Yeah. I mean, I didn't have to do the G type, but it's somehow interesting to be able to only sort of use part of this guy. Yeah.
What is the answer?
My proposed answer is I take the Coulomb branch, I multiply with the Langlands dual of G, and I mod out by these centralizers. And again, mod out means like in the affine scheme sense. And this seems to work in all the GLN cases, but at the moment, when G is trivial, when H is trivial, well, I think it still means what it says, right?
You take this ring object and compute that image on the Satake.
Yeah.
You're saying that it's equal to what?
right? So, let me just sort of tell you why I think this is remotely plausible. So-
I'm trying to understand what the statement. So if you just, so you have no H only G, right?
Yes,
So you take the our representation, you take, then you can construct a corresponding real object.
Yeah.
You want to produce its image on the direct subvector.
Yeah.
You're saying that's equal to what?
so
Equal-
it's the functions on the space where I take,
Coulomb branch, should do, what are you doing with that? You're multiplying by the group.
so I'm taking the product of the Coulomb branch and the group. That has a map to T mod W given by the integrable system, right? And,
Don't be.
okay, well, that's fair. It's a conjecture, I don't claim it's a theorem.
You know the relationship in all the directions, so you know how this image on the direction, like how to get the Coulomb branch.
Yeah.
It's just a restriction to positive slides. Right, and so I don't see any reason why I should be able to, in principle, restore the format from the left.
That's fair. So what is this? This is basically saying, yes, I know that it's pulled back to the constant slices. So let me take that and then spread that out using the action of GL. And you're absolutely right.
That's not the regular element. That's how, for some reason, you want to say, you're saying that you're somehow.
That's why we don't have a proof. Yeah, I mean, right, the claim has to be that this image under derived Satake has some sort of property where having the right thing that it, if you pull it back to the regular elements and then push forward, you get the same thing back. And maybe that's true, maybe it isn't. I'm not totally sure.
So is that exactly what it says? And how it's equal to.
So I think this is basically equivalent to that statement. Certainly, when I think about trying to prove it, that's the point where I get stuck. And that's why I put the question mark there. So this is something that when you pull it back to the constant section, gives you the right thing. But you have to worry there's. I mean, there's also some concern about like nothing here being derived, but I don't know. Somehow it seems to work out okay in these GLN cases, right? Well, I mean, like what this is saying in the GLN case is that, if you want some, if you have like a quiver guy, right, and you want to get the sheave, the push forward to the product of some GLNs corresponding to different nodes, you always take that node and you add a leg on it that's falling. Right, and I mean, in the case of one node, this is a theorem from your paper. It's optimistic. Okay. I prefer to say optimistic, but yeah. Well, it would be interesting to see if there's a counterexample. I certainly don't. I claim that it is an optimistic conjecture, but it's sort of, I don't know. I mean, we had made some very vague comment about this in the original version of the paper, and I exchanged some emails with Hiraku.
You mentioned the Satake, so you get an algebra, but it's an algebra over symmetric algebra check.
Mm-hmm.
And I'm saying that it's free with that.
Maybe. Probably that is a consequence, yeah. Yeah, I don't know. I will say Hiraku conjectured this to me in an email, sort of independently from, like we had said it in our paper, but I think we said it in a cautious enough way that he hadn't picked up on it, and he independently suggested it might be true. So, that's one piece of evidence, but maybe not the best piece of evidence.
But I have to run, actually.
Yeah. All right, bye.